Good evening and welcome to the stillness of the night, where the sky holds secrets and the world hums with quiet purpose. Tonight we'll drift through a world of satellites and time, where tiny clocks in the sky help us find our way. You'll meet the first GPS satellites launched in the late 1970s and the atomic clocks that tick with the rhythm of cesium atoms. You'll wonder how time, as Einstein showed, stretches and contracts in the sky, and how that helps you arrive exactly where you need to be. Let's settle in and let the story begin. The light has softened now, hasn't it? The sharp edges of the day are rounding, the colours deepening toward a stillness. If you look out across a field at this hour, the rows of crops seem to hold their breath, a vast green quiet stretching toward the horizon. And sometimes, moving slowly between those rows, you'll see a tractor, its driver guided not by landmarks or intuition alone, but by a small screen, a quiet hum of calculation that places him precisely within the larger pattern of the land. That's where we are tonight, in the heart of that quiet calculation, tracing the path of signals from the satellites in the sky. We call it GPS, of course, Global Positioning System, and it's become so woven into the fabric of our lives that we barely notice it anymore. A phone navigating a city street, a runner tracking a morning pace, a ship charting a course across the ocean. All of them rely on this network of orbiting clocks, a silent geometry unfolding above us. It's easy to think of it as magic, this ability to know your place on the earth with such precision. But like all magic, it has a story, a series of discoveries and refinements that brought it into being. And it begins, perhaps surprisingly, with a very old question. How do we know where we are? For centuries, that question was answered by careful observation, by the position of the stars, by the shape of the coastline, by the slow accumulation of maps and charts. But those methods were limited, dependent on clear skies and skilled navigators and prone to error. Then, in the mid-20th century, as the world began to look toward space, a new possibility emerged: to place a series of reference points above the Earth, to create a network of beacons that could be seen by anyone, anywhere. The United States Space Force now owns and maintains this system, operating it through a dedicated team known as Mission Delta 31. It is one of a growing number of what are called Global Navigation Satellite Systems, or GNSS, each nation building its own constellation to serve its own needs. Russia has its GLONASS, and China has been steadily developing its own system as well. But the first, the one that reshaped our understanding of place, was born here. The idea itself wasn't entirely new. During the Second World War, engineers began to explore the possibility of using radio signals to determine location. The principle is simple enough. If you can measure the time it takes for a signal to travel from a known point to an unknown point, you can calculate the distance between them. But the Earth is a complicated place, full of interference and atmospheric distortion, and the accuracy of those early systems was limited. It was only with the advent of the space age that the true potential of satellite-based navigation began to unfold. The first satellites, launched in the late 1970s, were experimental, bulky, and unreliable. But they proved the core concept, that it was possible to determine a position with reasonable accuracy using signals from orbit. And as the technology improved, the possibilities began to expand. It wasn't just about knowing where you were, but when as well. The satellites carried atomic clocks, incredibly precise instruments that could measure time with an accuracy of fractions of a second. These clocks, they measure time not by the tick of gears or the swing of a pendulum, but by monitoring the resonant frequency of atoms. Each atom has a unique energy signature, a set of quantized energy levels that define its behavior. Transitions between those levels happen at specific frequencies, and those frequencies are remarkably stable, unaffected by the vagaries of temperature or pressure. The SI definition of the second, the very foundation of our modern timekeeping, is now based on the phenomenon of atomic transitions, the unwavering rhythm of cesium atoms. Think for a moment about what that means. A farmer, guiding his tractor through a field, is relying on the stability of atoms, on the unchanging laws of quantum mechanics to determine his position. The screen on his dashboard is not just displaying coordinates, it's displaying the result of a profound scientific achievement, a testament to our ability to understand and harness the fundamental forces of the universe. But even with atomic clocks, the system wasn't perfect. The signals had to travel vast distances through the atmosphere, encountering delays and distortions along the way. And the Earth itself was not a static reference point, but a spinning, moving sphere. The satellites were orbiting at high speed, and the Earth was rotating beneath them, and both of those motions had to be accounted for. It was a complex problem, requiring a sophisticated understanding of physics and mathematics. And here is where the story takes a curious turn, a subtle complication that lies at the heart of GPS accuracy. The problem isn't just about measuring the time it takes for a signal to travel, but about understanding the nature of time itself. And to understand that, we need to go back to a German-born theoretical physicist named Albert Einstein. Einstein, born in 1879 and dying in 1955, revolutionized our understanding of space and time with his theories of relativity. He showed us that time is not absolute, but relative, dependent on the observer's motion and the strength of the gravitational field. Imagine two clocks, one stationary on the Earth's surface and one orbiting in a satellite. According to Einstein's theories, the clock in the satellite will tick slower than the clock on the Earth's surface. This isn't a matter of mechanical imperfection, but a fundamental consequence of the laws of physics. The satellite is moving at high speed, and that motion causes time to dilate, to stretch out. And the satellite is also in a weaker gravitational field, further contributing to the difference in time. The effect is small, only a few microseconds per day, but it's enough to throw off the calculations, to introduce errors in the positioning data. Without correcting for these relativistic effects, GPS would quickly become useless, inaccurate within a matter of minutes. And so, the satellites themselves are not just sending signals, but also carrying a tiny piece of Einstein's theories, a constant reminder of the subtle interplay between space, time, and gravity. The farmer, guiding his tractor, is unknowingly relying on the genius of a man who died decades before the first GPS satellite was launched, a testament to the enduring power of scientific discovery. This is, of course, a simplified picture. The actual calculations are far more complex, involving multiple satellites, sophisticated algorithms, and a constant stream of corrections. But the core principle remains the same. To determine your position, you need to know your distance from a series of known points, and to know your distance, you need to know the precise time it takes for a signal to travel between them. And to know the precise time, you need to understand the nature of time itself. The system operates independently of any telephone or internet reception. It is a self-contained network, a silent constellation orbiting above us, providing geolocation and time information to any receiver with a clear view of the sky. Satellite navigation, as it's called, provides coverage for any user on Earth, a global utility that has transformed our lives in countless ways. And it all began with a farmer, a tractor, and a quiet hum of calculation in a field, guided by the satellites in the sky. It's a remarkable thing, isn't it, how something so fundamental, knowing where we are, can lead to such profound discoveries, such intricate technologies, such a subtle connection to the workings of the universe itself. The light has softened now, hasn't it? A quiet blue settling over the edges of things, the kind that makes distances feel longer than they are, and the horizon a little less certain. If you close your eyes for a moment, you might imagine a vastness unfolding above, a network of signals tracing invisible paths across the dark. It's a stillness, this moment, but not an empty one. It's filled with movement, with information travelling at impossible speeds, with the constant hum of precision. We spoke last time of the quiet miracle that allows a tractor to follow a straight line across a field, guided by a constellation of satellites orbiting far above. It felt perhaps like a story of the sky, a gentle unfolding of how we came to know our place on the earth. And it was, in part. But the real story, the one that truly unlocks the precision of that line, lies in the dance between those satellites and the small receiver held in the hand or built into the dash of a vehicle. It's a dance of time, of distance, of constant calculation, a choreography performed on a scale almost too vast to grasp. To understand it, we must first think of position not as a place, but as a solution, a point defined not by what is there, but by how far away it is from other known points. Imagine, if you will, a single point suspended in space, utterly without reference. It could be anywhere, meaningless. But if you know its distance from another point, a second anchor, suddenly it is limited to the surface of a sphere. An infinite number of possibilities still remain, but they are all bound by that single measurement. Add a third anchor, a third distance, and the possibilities narrow further to the intersection of two spheres, a circle, and finally a fourth, and the point is resolved, a single location, pinpointed in 3 dimensions. This, at its heart, is trilateration, a method of determining an unknown position by measuring distances to known points. It's a concept that predates the satellites themselves, of course. Surveyors have used it for centuries, painstakingly measuring angles and distances with tools of brass and glass. But to apply it on a global scale, to achieve the accuracy required for navigation, demands a level of precision that was unimaginable until very recently. The 2nd Space Operations Squadron, part of the United States Space Force's Space Delta 8, maintains the constellation of satellites that make this possible. They are the silent guardians of the system, ensuring the continuous flow of signals that underpins so much of modern life. But the satellites themselves are merely the instruments. The true work is done by the signals they broadcast and the intricate calculations performed by the receiver. Each satellite is constantly transmitting a ranging signal, a precise burst of information that includes the time it was sent. The receiver, the small device in your hand, measures the time it takes for that signal to arrive, and from that time it calculates the distance to the satellite. It's a deceptively simple calculation. Distance equals speed multiplied by time. But the speed in question is the speed of light, and the times involved are measured in nanoseconds, billionths of a second. This is where the atomic clocks come in. These are not your grandfather's clocks, with swinging pendulums and delicate gears. They operate on a fundamentally different principle, harnessing the resonant frequency of atoms to measure time with extraordinary accuracy, specifically the transitions between energy levels within cesium atoms. An atom, you see, exists in discrete energy states, like steps on a ladder, and when it absorbs energy, it jumps to a higher step. When it releases energy, it falls back down. The frequency of the radiation required to trigger that jump is incredibly precise, a constant value that can be used as a timekeeping standard. The second, as we define it today, is based on these atomic clock measurements. It's not an arbitrary unit, but a fundamental property of the universe, defined by the oscillations of a cesium atom. Each satellite carries multiple atomic clocks, ensuring redundancy and accuracy. They are the heart of the system, the unwavering pulse that allows us to measure time with sufficient precision to determine our location on Earth. The receiver doesn't stop at 3 satellites. While 3 distances are enough to theoretically pinpoint a position, in practice it requires a 4th to correct for errors in timekeeping, and the more satellites it can lock onto, the more accurate the result. This is why the system is often called multilateration, a more accurate term when more than 3 distances are involved. But the signals aren't just ranging signals. They also include navigation messages, a continuous stream of data containing vital information about the satellite itself. This information includes the ephemeris data, which describes the satellite's precise orbit. Knowing the satellite's exact location is crucial for accurate trilateration. Without it, the calculations would be hopelessly inaccurate. The navigation messages also provide almanac information, detailing the status of all the satellites in the constellation. It's a complex data set, constantly updated and refined, ensuring the receiver has the most accurate information available. There are in fact 4 different GPS signal specifications currently in use for civilian applications. The L1CA signal is the legacy signal, broadcast by all operational satellites. It's the oldest and most widely available, but also the least accurate. The L2C, L5 and L1C signals are modernized signals, only broadcast by newer satellites. They offer improved accuracy and resistance to interference, but require more sophisticated receivers. The receiver, then, is not simply a passive recipient of signals. It's an active participant in the dance, constantly processing data, correcting for errors, and refining its calculations. It's a remarkable feat of engineering, packing a tremendous amount of processing power into a small, portable device. The distances calculated from the signal travel times aren't Euclidean, straight-line distances either. The Earth is a sphere, and signals travel through the ionosphere and troposphere, bending and slowing as they pass through these layers of the atmosphere. The receiver must account for these effects, using complex models to estimate the true distance to each satellite. This is a significant source of error, and ongoing research is focused on improving these atmospheric models. The receiver is also constantly updating its position, using a technique called Kalman filtering. This is a recursive algorithm that estimates the state of a system, in this case the receiver's position and velocity, based on a series of noisy measurements. It combines the latest measurements with previous estimates, weighting them according to their accuracy. This allows the receiver to smooth out errors and provide a more stable and reliable position estimate. So you have this network of satellites, each broadcasting a precise signal containing information about its location and the time it was sent. You have a receiver constantly measuring the travel time of those signals and calculating the distance to each satellite, and you have a complex algorithm refining those calculations and correcting for errors. But even with all this precision, there's still one fundamental problem that must be addressed. The signals are traveling at the speed of light, and light, as we now know, is not constant. It's affected by gravity, and the satellites orbiting far above the Earth experience a different gravitational field than the receiver on the ground. This means that time itself is flowing differently for the satellites than for us. The satellites' clocks run faster than clocks on Earth. And if these relativistic effects weren't accounted for, the GPS system would quickly become inaccurate, drifting by several kilometers per day. This, of course, is where the deeper story begins, the story of special relativity and the subtle distortions of time and space that underpin our understanding of the universe. But that is a tale for another time. For now, suffice it to say that the satellites and the receivers are constantly correcting for these relativistic effects, ensuring the accuracy of the system. The process, then, is not simply a matter of measuring distances. It's a complex interplay of time, gravity, and motion, a constant negotiation between the satellites and the receiver, a silent dance performed on a global scale. And it's a dance that allows us to know our place on Earth with a precision that was unimaginable just a few decades ago. It's a testament to the power of human ingenuity and the profound connection between everyday technology and the fundamental laws of the universe. The calculations, constantly unfolding, are not just about determining where we are, but about understanding the very fabric of reality. The receiver, small and unassuming, is a window into a deeper world, a world governed by the laws of physics and the unwavering precision of atomic clocks. And as the satellites continue their silent orbit, broadcasting their signals across the sky, they remind us of the interconnectedness of everything and the subtle forces that shape our lives. It is a quiet and relentless work, this dance, a subtle and profound act of measurement that continues unseen with every passing moment. The world, as it turns, is known with ever greater certainty. The light has softened further, hasn't it? A quietness settling in, a deepening of the blue beyond the window. If you trace the line of the horizon, you'll find it's not a sharp division, but a gradual dissolving, a place where one thing becomes another. And that dissolving, that subtle shift in definition, is where the story truly begins, not in the bright clarity of a single point, but in the edges, in the places where certainty gives way to something more complex. We spoke last time of the silent conversation between the satellites and the receiver, the precise exchange of signals that allows us to know our place on the Earth. That exchange, that dance, relies on a fundamental assumption, that time flows equally for everyone. A second here is a second there, a tick of the clock on the ground mirroring the tick of the clock orbiting high above. It is an assumption we make instinctively, woven into the fabric of our everyday experience. And for most purposes it holds true, but it isn't quite so simple. Imagine for a moment the clock on that satellite suspended in the vastness of space, and the clock here on Earth anchored to the turning sphere below. They are both measuring the same thing, the passage of time, but they are doing so within profoundly different conditions. The satellite is moving, traveling at a considerable speed relative to us, circling the Earth again and again. And the Earth itself is spinning, rotating, accelerating. It's a subtle motion, almost imperceptible in our daily lives, but it's there, a constant, gentle force, and it matters. It began, as so many things do, with a thought experiment. A ship, Galileo Galilei proposed in 1632, moving smoothly across a calm sea. If you were inside that ship, sealed away from any external reference point, how could you possibly tell whether you were at rest or in motion? You could walk, you could drop an object, you could pour a glass of water. Everything would behave exactly as it would if the ship were stationary. The principle of relativity, he called it. The laws of physics are the same for all observers in uniform motion. It's a deceptively simple idea, but it has profound consequences. If motion itself cannot be detected from within a closed system, then there is no absolute frame of reference, no fixed point against which to measure the speed of anything else. And if there is no absolute frame of reference, then the very notion of absolute time begins to unravel. This idea lay dormant for centuries, a philosophical curiosity. It wasn't until the late 19th and early 20th centuries that it began to take on a concrete mathematical form. Joseph Larmor, in 1897, was studying the behavior of electrons orbiting a nucleus. He noticed something peculiar. The ratio of times seemed to change depending on the speed of the electron. A fast-moving electron appeared to experience time more slowly than a stationary one. This wasn't a statement about the electrons themselves, but a mathematical consequence of the way we describe motion and electromagnetism. Emil Cohn, a few years later in 1904, took this further, showing that the same effect applied to clocks themselves. Clocks moving at high speeds would tick more slowly than clocks at rest. This wasn't a flaw in the clocks, but a fundamental property of space and time. The faster you move, the slower time passes for you, relative to someone who is standing still. And then, in 1905, came Albert Einstein, who brought these disparate threads together into a unified theory. He called it the special theory of relativity, and it rested on two simple postulates. The first, Galileo's principle, we've already touched on. The laws of physics are the same for all observers in uniform motion. The second, more radical, the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source. These two postulates, seemingly innocuous, have astonishing consequences. They imply that space and time are not absolute but relative, intertwined into a single fabric called space-time, and that fabric can be warped and stretched by motion and gravity. What does this mean for our clock on the satellite? It's moving at roughly 14,000 kilometers per hour, a considerable speed, and because of this motion, time passes more slowly for it than for the clock on Earth. The difference is small, incredibly small, a matter of nanoseconds per day, but it's there. Without accounting for this effect, the GPS system would quickly become useless, accumulating errors of several kilometers per day. The atomic clocks are the key to this precision. They don't measure time by the fall of a pendulum or the flow of sand, but by the resonant frequency of atoms. Atoms, it turns out, have a natural tendency to oscillate at specific frequencies, like tiny, perfectly tuned tuning forks. These frequencies are incredibly stable, unchanging, providing a reliable measure of time. The SI definition of the second, in fact, is based on the phenomenon of atomic transitions. It's defined as the time it takes for 9,992 31,070 oscillations of the cesium-133 atom. It's a remarkably precise definition, allowing us to measure time with an accuracy of better than a billionth of a second. But even these incredibly precise clocks are not immune to the effects of relativity. The satellite's clock, orbiting high above the Earth, experiences not only time dilation due to its velocity, but also time dilation due to its gravitational potential. The farther you are from a massive object, the slower time passes for you. The satellite is farther from the Earth's center of gravity than we are, and therefore experiences time more quickly. These two effects, velocity time dilation and gravitational time dilation, work in opposite directions. Velocity time dilation slows down the satellite's clock, while gravitational time dilation speeds it up. The net effect is a slight speeding up of the satellite's clock, about 38 microseconds per day. This might seem like a trivial amount of time, but it's enough to throw off the entire system. If we didn't correct for this effect, our GPS receivers would be off by about 10 kilometers per day. The engineers who designed the system had to account for these relativistic effects with meticulous care, incorporating them into the software that governs the satellites. And that perhaps is the most remarkable thing about GPS. It's not just a technological marvel, but a practical demonstration of some of the most profound and counterintuitive theories in physics. Every time you use your phone to navigate, you are relying on a system that depends on the fact that time is not absolute, but relative, that space and time are intertwined, and that the universe behaves in ways that are far stranger and more wonderful than we could ever have imagined. It's a subtle correction, a quiet adjustment made by the software, but it's essential. It's a reminder that even the most mundane technologies are built on a foundation of deep and complex science. The system wouldn't work without it. The signal would drift, the location would be wrong, and the precision we take for granted would vanish. Consider for a moment the thought experiment again, the ship moving smoothly across the sea. It's a closed system, isolated from any external reference point. But the universe is not a closed system. It's vast and interconnected, filled with forces and energies that we are only beginning to understand. And our perception of time is not absolute but relative, shaped by our own motion and position within this vast and complex universe. This idea, this unsettling notion that time is not what we think it is, has found its way into our culture, into our art and literature. In Jorge Luis Borges's short story, The Garden of Forking Paths, the protagonist explores a labyrinthine world where time branches and diverges, creating infinite possibilities. It's a fictional exploration of the same idea that Einstein described, that time is not a linear progression, but a complex network of possibilities shaped by our choices and actions. The story isn't about the plot, of course. It's about the underlying idea, the sense that time is not fixed but fluid, that the future is not predetermined but open and uncertain. It's a feeling that many of us have experienced, a sense that there are other paths we could have taken, other lives we could have lived. And it's a feeling that is rooted in the same scientific principles that govern GPS. The system itself is a complex interplay of signals, algorithms, and corrections. The satellites are constantly broadcasting their position and time, and the receivers on the ground are constantly measuring the time it takes for these signals to arrive. The software then uses this information to calculate your position, taking into account the effects of relativity and atmospheric interference. It's a delicate dance, a constant exchange of information, a subtle choreography of forces. And it all relies on the fact that time is not absolute but relative, that space and time are intertwined, and that the universe behaves in ways that are far stranger and more wonderful than we could ever have imagined. It's a quiet revolution, a subtle shift in our understanding of the universe, and it's happening every time you use your phone to find your way home. The precision you feel is not just about the technology, but about the deeper, underlying structure of space-time itself, a structure that resists easy measurement, that challenges our intuition, and that continues to reveal its secrets slowly, patiently, over time. The clocks on those satellites, orbiting high above us, are not simply measuring the passage of time, they are measuring the very fabric of the universe, a fabric that is constantly shifting and changing, a fabric that is woven together by the forces of gravity and motion. And as we continue to explore this fabric, to unravel its mysteries, we will inevitably discover new and unexpected wonders, new and unexpected challenges. The exploration of time, it seems, is a journey without end, a journey that will continue to push the boundaries of our understanding for generations to come. The light in the laboratory has softened further, the sharp edges of the instruments dissolving into a gentle glow. There is a stillness here, a quiet hum that isn't silence exactly, but the absence of urgency. The air itself feels weighted, not with dust or heat, but with the sheer concentration of measurement. It's a room built for patience, for the slow accumulation of certainty from the almost imperceptible shifts in the world. We are surrounded by clocks, not the kind that mark the passing of hours with a tick and a hand, but instruments that measure time itself, dissecting it into fractions so small they barely exist. And yet, upon those fractions rests the stability of a world you carry in your hand. These are atomic clocks, and their story begins, as so many stories do, with a question of precision. For centuries, humankind had relied on the movements of the earth, the predictable arc of the sun, to define its days and years. But as the need for finer and finer accuracy grew, it became clear that these methods were insufficient. The pendulum, the most refined mechanical timekeeper of its age, was still subject to the subtle variations of temperature, air pressure, even the pull of the moon. To truly understand time, to truly measure it, one had to look beyond the macroscopic world to the realm of the atom. The principle is deceptively simple. Certain atoms, when isolated and cooled to near absolute zero, possess specific energy levels. They can exist in one state or another, and transitions between these states require a precise amount of energy in the form of electromagnetic radiation. It is the frequency of this radiation, the number of oscillations per second, that defines the atom's resonant frequency, and that frequency, unchanging and universal, becomes the basis of our most accurate timekeeping. The cesium-133 atom, in particular, proved to be remarkably stable, its resonant frequency serving as the foundation for the modern definition of the second. Imagine, if you will, a vessel, a vacuum chamber, sealed and shielded from any external interference. Inside, a stream of cesium atoms is heated, causing them to vaporize. A series of magnets then separates the atoms based on their energy states. A microwave cavity is tuned to the precise resonant frequency of cesium-133, and as the atoms pass through it, those in the lower energy state absorb the radiation and transition to a higher state. A detector then measures the number of atoms that have made this transition. The frequency of the microwaves is adjusted until the maximum number of atoms absorb the radiation, indicating that the cavity is perfectly tuned to the atom's resonant frequency. This isn't a single event, a one-time calibration. It's a continuous process, a constant feedback loop. The detector sends a signal to a control system, which adjusts the microwave frequency in real time, maintaining the perfect resonance. The process repeats itself billions of times per second, each oscillation a tiny increment of time meticulously counted and recorded. The resulting signal is then used to drive a quartz crystal oscillator, which generates a stable frequency that can be used to measure time with incredible precision. James Van Allen, whose name is linked to the belts of energetic particles that encircle our planet, didn't work directly with these clocks, but his discoveries were essential to understanding the environment in which they operate. Born September 7, 1914, he dedicated his life to the study of the Earth's magnetic field, and in 1958, with data gathered from the Explorer 1 satellite, he revealed the existence of these radiation belts, zones of charged particles trapped by the Earth's magnetic field, a phenomenon that would profoundly impact the design and operation of GPS satellites. He continued his work at the University of Iowa until his death on August 9, 2006, leaving behind a legacy of exploration and discovery. The radiation belts are a constant source of interference for the atomic clocks on board the satellites. These energetic particles collide with the atoms, disrupting their resonant frequency and introducing errors into the time measurements. To mitigate this effect, the clocks are shielded with layers of protective material, and complex algorithms are used to compensate for the remaining errors. But even with these precautions, the effects of the radiation belts are significant, and they must be accounted for in the precise orbit determination process. Orbit determination is the art and science of calculating the position of an object in space. For a satellite, this is a remarkably complex task. It's not simply a matter of tracking its position at a single point in time. The satellite is constantly moving, influenced by a multitude of forces: the Earth's gravity, the gravitational pull of the Sun and Moon, the pressure of solar radiation, even the subtle drag of the Earth's atmosphere. To accurately determine its orbit, one must account for all of these forces, and that requires a constant stream of observations. These observations are raw data, signals received from ground stations around the world. The signals contain information about the satellite's position and velocity, but they are also noisy and incomplete. The task of orbit determination is to filter out the noise, fill in the gaps, and construct a model of the satellite's orbit that is as accurate as possible. This is done using sophisticated algorithms, mathematical equations that take into account all of the known forces and constraints. Imagine a room filled with data streams, each one representing a single observation of the satellite's position. The data comes in at a constant rate, a torrent of numbers that must be processed and analyzed in real time. The algorithms sift through the data, identifying patterns and anomalies. They calculate the satellite's position at each point in time, and then they use those positions to predict its future trajectory. The prediction is then compared to the actual observations, and the algorithms adjust the model accordingly. This isn't a single calculation, a one-time prediction. It's an iterative process, a constant refinement of the model. The algorithms repeat the process billions of times per second, each iteration bringing the prediction closer to reality. The resulting orbit is then used to calculate the satellite's position at any given point in time with an accuracy of just a few centimeters. The precision of this process is astonishing. It allows us to track newly observed asteroids, to predict their trajectories, and to assess the risk of collision with Earth. It allows us to send probes to distant planets, to navigate them through the vastness of space, and to land them safely on alien worlds. And it allows us to maintain the accuracy of the global positioning system, the network of satellites that guides us through our everyday lives. The atomic clocks on board the satellites are not merely timekeepers. They are the foundation of this entire system. They provide the reference signal, the stable baseline against which all other measurements are made. But they are also subject to the effects of relativity, the subtle distortions of time and space that Einstein predicted over a century ago. To understand these effects, one must delve into the heart of the atom itself. The energy levels of an atom are not fixed. They are affected by its motion and its gravitational potential. As a satellite orbits the Earth, it is constantly moving at high speed, and it is also experiencing a weaker gravitational field than an observer on the ground. These two effects, the velocity and the gravity, have opposite effects on the atom's resonant frequency. The velocity causes the frequency to decrease, while the gravity causes it to increase. The net effect is a subtle but measurable difference in the time experienced by the clocks on board the satellites compared to the clocks on the ground. This difference is on the order of 38 microseconds per day, a tiny fraction of a second, but it is enough to throw off the entire GPS system if it is not accounted for. The algorithms that compensate for these relativistic effects are remarkably complex. They take into account the satellite's position and velocity, the Earth's gravitational field, and even the subtle effects of the satellite's own motion on its clock. The result is a correction factor that is applied to the time measurements, ensuring that the GPS system remains accurate to within a few meters. This correction is not merely a theoretical adjustment. It is a practical necessity, a fundamental requirement for the operation of the entire system. The instruments here are not merely tools, they are extensions of our senses, allowing us to perceive the subtle nuances of time and space. They are a testament to our ingenuity, our ability to overcome the limitations of our own perception and to unravel the mysteries of the universe. And they are a reminder that even the most fundamental concepts, time, space, gravity, are not as straightforward as they seem. The laboratory hums, a quiet resonance, a constant reminder of the unseen forces that shape our world, and the relentless pursuit of precision that drives us forward. It is a quiet, almost imperceptible shift, a measure of how much we do not yet know, and the endless possibilities that lie ahead. The data continues to flow, each signal a tiny increment of understanding, a step closer to a more complete picture of the universe we inhabit. The algorithms refine, the clocks tick, and the world, held in a delicate balance, continues to turn. The light in the room has softened further, a gradual dimming that seems to hold the very air still. It isn't a darkness that obscures, but one that deepens the focus, a quietening of everything that isn't essential. Outside, if there is an outside here, the world continues to turn, but its momentum feels distant, a gentle hum rather than a pressing force. We've been tracing the path of signals, the invisible threads connecting a constellation of satellites to the small device in your hand, or the dashboard of your car, or the watch on your wrist. And in doing so, we found ourselves drawn into a deeper question, a subtle but profound reshaping of our understanding of the universe itself. It began, as so many things do, with a discrepancy. A tiny, almost imperceptible disagreement between clocks, not the grand, sweeping differences of early navigation, where longitude remained a stubborn mystery for centuries, but something far more delicate. Clocks aboard commercial airliners, flown eastward and then westward around the world, returning to the stillness of the United States Naval Observatory, showed a variance in their recorded time. A variance so small it would be meaningless in the everyday rhythm of life, but one that when measured with the unwavering precision of atomic resonance demanded an explanation. This was the work of Joseph C. Haffel and Richard E. Keating, a physicist and an astronomer whose experiment, conducted in 1971, brought the abstract equations of Albert Einstein into the concrete reality of global navigation. The atomic clocks themselves are remarkable instruments, each one a miniature universe of controlled motion. They don't measure time as a flowing river, but as the unwavering pulse of an atom. Specifically, the cesium-133 atom, chosen for its predictable transitions between energy levels. Imagine a tiny self-contained world where electrons orbit the nucleus with a precise frequency like a miniature planet circling a sun. To measure time, these atoms are cooled to near absolute zero, slowing their motion until only the fundamental vibration remains. Then they are exposed to microwaves, carefully tuned to match the resonant frequency of the atom. When the frequency is perfect, the atom absorbs the energy, shifting to a higher energy level. Detectors monitor these transitions, counting each pulse with unwavering accuracy. The SI definition of the second, the very foundation of our modern timekeeping, is based on this resonant frequency. 9,192,631,770 cycles of radiation corresponding to the transition between two energy levels in the cesium-133 atom. But even this perfect isolation isn't enough. The clocks are not merely measuring time, they are moving through time, through space, and subject to all the forces that govern those realms. And it was here, in the subtle interplay of motion and gravity, that the discrepancies began to appear. The eastward flying clocks, traveling in the same direction as the Earth's rotation, experienced a slight slowing of time, as predicted by special relativity. The westward flying clocks, traveling against the rotation, experienced a slight speeding up. These effects were minuscule, measured in nanoseconds, but they were real, and they were consistent with the equations that Albert Einstein had published in May 1916, the foundation of what we now understand as general relativity. General relativity, in its simplest form, describes gravity not as a force, but as a curvature of space-time. Imagine a stretched sheet of fabric representing the universe, and place a heavy ball in the center. The fabric dips and curves around the ball, creating a well. Now roll a smaller marble across the sheet. It won't travel in a straight line, but will curve towards the heavier ball, as if drawn by an invisible force. That curvature, that bending of space-time, is what we experience as gravity. And it isn't just massive objects like planets and stars that create this curvature. Even the Earth itself, with its constant rotation and its complex distribution of mass, warps the fabric of space-time around it. And because time is interwoven with space, this curvature affects the passage of time itself. The closer you are to a massive object, the slower time flows. This isn't a matter of perception, but a fundamental property of the universe. An atomic clock on the surface of the Earth, closer to the planet's mass, will tick slightly slower than a clock in orbit, farther from the gravitational well. The effect is tiny, but it's measurable, and it's crucial to the accuracy of GPS. This brings us back to the Quiet Constellation of satellites, each one a precisely calibrated instrument, orbiting the Earth at an altitude of roughly 20,000 kilometers. Each satellite carries multiple atomic clocks, constantly broadcasting their precise time. Your GPS receiver on the ground doesn't measure distance directly, but time. It calculates the distance to each satellite by measuring the time it takes for the signal to arrive. But to do this accurately, it must account for the effects of both special and general relativity. The satellites are moving at high speeds relative to the Earth, experiencing time dilation due to their velocity, and they are in a weaker gravitational field than the Earth's surface, experiencing a different rate of time flow. Without these corrections, the GPS system would quickly become inaccurate, drifting by several kilometers each day. The precision we take for granted, the ability to navigate with pinpoint accuracy, relies on a subtle but profound understanding of the universe, a universe where time is not absolute but relative, where gravity is not a force but a curvature, and where the very fabric of space-time is warped by the presence of mass and motion. The process of accounting for these relativistic effects is known as orbit determination. It's a complex algorithm, a continuous feedback loop of observation and correction. Ground stations around the world constantly monitor the satellites, tracking their position and velocity with incredible accuracy. These observations are fed into the orbit determination algorithms, which calculate the precise orbits of the satellites, taking into account all the known forces acting upon them: the Earth's gravity, the gravitational pull of the Sun and the Moon, the drag of the upper atmosphere, and, crucially, the effects of relativity. The algorithms then predict the position of each satellite at any given moment in time and transmit this information to your GPS receiver. Think of it as a delicate dance, a choreography of signals and calculations, a silent conversation between the satellites and the Earth. The satellites broadcast their time, the receiver measures the time it takes for the signal to arrive, and the orbit determination algorithms correct for all the subtle variations in time flow, ensuring that the system remains accurate. This isn't a simple calculation, but a continuous process of refinement, a constant adjustment to the ever-changing conditions of space. It's a testament to the ingenuity of human engineering, a remarkable feat of precision and collaboration. And it's a reminder that our understanding of the universe is constantly evolving. The equations that Einstein published over a century ago weren't just theoretical abstractions, but real tools capable of predicting the behavior of the world around us with incredible accuracy. The Heffel-Keating experiment, with its tiny discrepancies between clocks, wasn't just a scientific curiosity, but a validation of Einstein's theory, a confirmation that time is not absolute but relative. The orbit determination algorithms, with their complex calculations and continuous corrections, aren't just technical marvels, but a testament to our ability to understand and harness the fundamental forces of the universe. The satellites themselves, circling silently above us, are not just instruments, but witnesses. They are constantly observing the Earth, measuring its shape, its gravity, its magnetic field, and transmitting this information back to us. They are a silent constellation, a network of sensors, a window into a deeper world. And as they continue to orbit, they are constantly refining our understanding of the universe, pushing the boundaries of our knowledge and challenging our assumptions. The beauty of this system, perhaps, lies in its quietness. It operates unseen, unnoticed, a subtle hum beneath the surface of our lives. We rarely think about the complex calculations and continuous corrections that allow us to navigate with pinpoint accuracy. We simply rely on the system, trusting that it will work, and it does, with remarkable precision. This is the power of science, the ability to understand and harness the fundamental forces of the universe, to create tools that improve our lives, and to do so with quiet elegance. And it's a reminder that there is still much we don't know. The universe is vast and complex, full of mysteries waiting to be unraveled. The equations that Einstein published over a century ago are still being refined, still being challenged, still being used to explore the deepest questions of existence. The orbit determination algorithms, with their continuous corrections, are constantly being improved, still striving for greater accuracy, still seeking to understand the subtle variations in time flow. The satellites themselves, circling silently above us, are constantly transmitting information, still revealing new insights into the nature of our world. The precise interplay of gravity and motion, the delicate balance between space and time, remains a source of wonder, a puzzle that continues to challenge and inspire us. The signal from the satellite reaches you now, a faint whisper across the vastness of space. It's a testament to the power of human ingenuity, a reminder of our ability to understand and harness the fundamental forces of the universe. It's a connection to something larger than ourselves, a silent conversation with a constellation of witnesses. And it's a moment of quiet precision, a subtle hum beneath the surface of our lives. The small device in your hand, or the dashboard of your car, or the watch on your wrist is not just a tool, but a window into a deeper world, a connection to the silent rhythm of the universe. And in that rhythm, in that quiet constellation, there is a sense of peace, a sense of wonder, a sense of belonging. The satellite continues its orbit, a small point of light against the darkness, a silent guardian, a constant witness, and the signal continues to reach you, a faint whisper across the vastness of space, carrying with it the quiet promise of precision, the subtle hum of understanding, and the gentle reassurance that even in the face of complexity, there is a sense of order, a sense of beauty, and a sense of connection. It is a steady, unwavering pulse, a resonant frequency, a constant reminder of the fundamental forces that shape our lives, and as it reaches you now, it settles like starlight into the quiet fabric of the night. The satellites hum in their orbits, their clocks ticking in perfect sync. Mission Delta 31 keeps them running far above the Earth. Cesium atoms pulse inside those clocks, measuring time with quiet precision. Einstein's math made it all possible. Time slows for the satellites, but they adjust for it. The Second Space Operations Squadron watches over the whole network, ensuring signals reach your phone or car. They float in silence, high above, sending down a steady stream of data. The world below moves, but they stay still. Their signals fade into the air, soft and constant. The sky holds them, steady and true. Their clocks keep ticking, calm and sure. The Earth turns, but they stay where they are.